says evaluate the partial derivative. So how does entropy with respect to specific volume change at constant temperature for the substance propane at a fixed temperature and a fixed specific volume? Pressure, temperature, specific volume, entropy. So the pressure was in bar, and it was 6 bar. And the temperature in degrees C, it was 20 degrees C. The specific volume in meters cubed per kilogram, 0.08187. And the entropy corresponding is 1.815 kilojoules per kilogram Kelvin. Okay? You want to get how does S change as I change specific volume along a line of constant temperature. True? And so you think, okay, well, I have this value for V, 0.08187, and I have this value for S, 1.815, and I need to get a value maybe a little below it and a little above it, but I need to stay at the same temperature of 20 degrees C. Well, go to another pressure block, maybe go to the pressure block of 5 bar, 20 degrees C, and we look up the specific volume, 0.1005, and the entropy, 1.858. Likewise, maybe we go to the pressure block above, 7.0, 20 degrees C, 0.06847 for the propane, and 1.776. So you just picked off 2 values like that. You could do it from just using these 2 points right here. True? So it's how the change in S divided by the change in V, the slope of that line. So the partial of S with respect to V at constant T would be this, you want to call this 0.2 and this 0.1. So it'd be S2 minus S1 divided by V2 minus V1, true? Where those points are all at the same temperature. You could also call this 0.3, and maybe you say it's also approximately equal to, because they're going to get a slightly different answer, S3 minus S2 divided by V3 minus V2. Both of those will work. If I did it with this set, I got the value 2.308. With this set, 2.91. What do you want to do? I weighted them, and you get about 2.658. What are the units on that? Well, it's the units of the change in entropy, kilojoules per kilogram Kelvin, per the change in specific volume, meters cubed per kilogram. So it does reduce a little bit. So you have kilojoules per Kelvin meter cubed. You can even reduce those units even further, true? 2.658. What is a kilojoule? Is it a kilopascal meter cubed? Kilopascal per Kelvin. So that's a good numerical approximation. What's another way of doing this? One other way of doing it would be trying to use one of the relationships that we covered in the text, which was the Maxwell relationship, that the rate of change of S with respect to V holding T constant is equal to the rate of change of P with respect to T holding V constant. Maybe it's easier to calculate this derivative. And if it is, then that's equal to the other derivative that you're looking for, the derivative of interest. We can use the Redlich-Kwong equation of state, which is given by P is equal to R bar T divided by V bar minus B minus A divided by V bar times V bar plus B times T to the 1/2. Where do I get those constants A and B? They're in the back of the textbook in a table, A24. So you can look up the coefficient A in the Redlich-Kwong equation. A is equal to 182.23 in the units of bar, meters cubed per kilomole, quantity squared, times Kelvin to the 1/2 power. And then the coefficient B, 0.06242 units of meters cubed per kilomole. What do we do here is you take this equation and you see if you can't analytically calculate the derivative of pressure with respect to temperature holding specific volume constant. So you get R bar divided by V bar minus B, true, for the first part. A, V bar plus B. Now you have to differentiate that. So you get a minus 1/2 times T to the negative 3/2, or 1 over T to the 3/2. And then it's plug and chug. So you plug in the value of B, you plug in the value of A. V bar, just a little bit of work. We have to look up the molar mass of propane, which is 44.09 kilograms per kilomole. And then you have all of the V bars. Okay, what about the R bar? What is that? 8.314, true? But watch your units, because 8.314 kilojoules per kilomole Kelvin. And then the temperature, it's evaluated at 20 degrees C, so the temperature is 273 plus 20, 293 Kelvin. When you do that, watch out for units. A bar is 100 kilopascal. And you'll get that this derivative dp dt at constant v using the Redlich-Kwong equation of state is equal to, let me deal with this here, is equal to 2.481 units kilopascal per Kelvin. So how do they compare? It's about 8% difference. It's 8% lower from the values in the tables. I wouldn't recommend such a coarse equation of state. This is just an approximation, the Redlich-Kwong, as well as the approximation to the numerical derivative. So, but it gives you a sense of how things are put together in this chapter. True?